data collection, assumption tests, outliers, multiple comparisons, statistical significance, and finally, statistical method selection. So let's get started here. So the number one mistake that I wanted to cover is the level of measurement on which you collect your data. This might seem like an overly simplified one, but I've actually seen it happen before, and it is a huge headache to deal with if it ever happens to you. So what I mean by aggregate level versus unit level here is the observational units that you're actually collecting your data on. So you can think of an observational unit as a person, or it might be a point in time, or it might be a particular location if you're dealing with schools or something like that. Really what it is it's just something that you're using to quantify your actual outcome measures. And so that can take on different forms. It's not necessarily an individual, but the key thing here is sample size. So in this instance, you can look at the image at the bottom of this slide. I've chosen just individuals. And so each individual gets an ID, and as you can see on the left, this would be considered a unit level data, because as you can see, I've got up to 75 individual users, and I've broken up the table there so that I didn't have to list them all. And you can see that for each individual, I have a marital status, 0 if they're not married and 1 if they are, and then I have a monthly housing expense for each individual. This is extremely important for some types of questions you might want to ask about using this data. Aggregate data, on the other hand, is when you take unit level data and you calculate some kind of summary statistics on it, and then you end up with just that. You end up with summary statistics, really. And so you can see on the right-hand side of that image that you've got an entire group of married men, and then all you have is a single number for that group, and the same for single men. This might be a problem because if you wanted to do some inferential statistics, you suddenly are missing a lot of information. You don't have any variability. You don't have any information about sample size, for example. And you might have these things, and it's true that some statistical analyses you may be able to take aggregate data if you have enough of it and be able to perform some kind of an analysis, but in most cases you can't ever get back to that original unit data, which has the most information. And remember, you can always take unit data and calculate aggregate data from it, but you can never go the other way around. So just be really careful when you're designing your studies to make sure that you think through the type of data that you're going to need and the question that you want to answer, and just make sure you design your data collection scheme around getting data that will help you achieve that goal, as opposed to ending up after months of hard work with data that actually can't even help you answer your question. It's a very easy mistake to make for some, and you definitely want to avoid making that. So for the second mistake that I've decided to talk about would be over-interpreting assumptions. This might be not such a familiar concept for a lot of you. I'm sure in introductory statistics courses they definitely cover how it's important to test for assumptions, and it definitely is. I'm not suggesting that assumptions are not important, and I'm not suggesting that you shouldn't evaluate the assumptions before you conduct your test. But what I am saying is that sometimes, especially with the sample sizes that we deal with today, assumptions can lead to a little bit of confusion about what an assumption is actually for and what it actually means for your analysis. To illustrate that, why don't we consider the case of testing normality, which is common with analyses like linear regression or t-tests or the ANOVA type of analyses. The problem with testing normality using a hypothesis test is that as the sample size increases, it requires smaller deviations from perfect normality that will actually give you a significant result. This is a problem because it might cause a researcher to dismiss an analysis that would have otherwise been perfectly valid. Take a look at the scatter plot on the left. This is called a QQ scatter plot. QQ stands for quantile, quantile. And what this does is it plots the sample quantiles of your data against those of a normal distribution. And so if everything lines up, it should form a perfectly straight diagonal line, which is what we see here. I generated this data, so I happen to know that it did come from a normal distribution. And as we look at the plot, we can see, maybe some slight deviations, but definitely nothing to be alarmed about. I mean, this is, for all intensive purposes, perfectly normal data. Yet when we run a Shapiro-Wilk test on this data, we see a significant p-value. So this is an instance in which perhaps not proceeding with a linear regression or a t-test based on this data would probably not be the right choice, because for all practical purposes, the results will be completely unaffected by the violation of normality that the Shapiro-Wilk test claims that is present. So visual methods aren't always perfect, and a lot of times there's subjectivity involved in interpreting them, but it's one of those things where using a yes or no decision based on a hypothesis test is probably worse in the long run. And by all means, use both, but just be sure that you're evaluating the assumptions on a more general level as well. So the third mistake is kind of a complicated one. It's a common practice in many fields to remove extreme observations to clarify or maybe make the results seem a little more accurate. I may be a little biased about this because I personally think it's a terrible practice in most cases, but you know, nonetheless, it still happens. And I'd like to just talk about deleting outliers for a little bit and explain why I don't think it's a very good method. So, as you all probably know, remember that data really are they just come from a statistical model. A statistical model is something that produces data. That's a very important statement. What that means is that given a regression model or an ANOVA equation or something of that nature, all that means is that you plug numbers in and out comes data. So any sample that you've ever seen, any real life data, has a data generating process associated with it. There is some underlying process that produced that data. So if we're trying to understand that data or analyze that data in some way, then the best model is going to be a model that produces data like the data that we observed. So in other words, if the sample that we have contains outliers or extreme values, then we should probably assume that the underlying data generating process also occasionally produces extreme values. With that in mind, if we're going to try and analyze this data with a parametric method, we should probably select a model that also produces these extreme values. That's not necessarily what you see all the time. Sometimes you see researchers trim the edges, so to speak. They'll delete some of these extreme observations, which tends to give you maybe a significant regression model, but one that doesn't really produce data that looks like the true data generating process. And so what you end up with is a false model. You start basing claims or making generalizations based on this model, you might find yourself in trouble. So one alternative to using parametric methods that might be affected by outliers is just to use a non-parametric method instead. They're generally more stable, not quite as affected by outliers or other assumption violations for that matter, and in the case when the assumptions are violated, they're actually more popular, or more powerful. To illustrate why this might be a problem, consider the following two scatter plots. So on the left, you can see that there's an extremely low Y observation there, and I've labeled it as an outlier with an arrow pointing to it. And then below this scatter plot, I've performed a linear regression, and I've listed out the results of that. And what we can see here is that we actually don't have a significant result. It's showing that we have an estimate of 0.15, and the p-value for that estimate is 0.08, which would be above any reasonable cutoff in most cases. However, on the right side, I've deleted this outlier and run the exact same regression. And now we see a highly significant result. So it seems a little odd to me that deleting one value could produce such a large difference in significance, but it happens. And this is something you really want to watch out for, because in reality, there's probably no difference here, as you can see from the scatter plot looking relatively straight. Yet when you tweak the data or remove certain values, it can be really easy to want to do that because it makes your results seem more significant than they are, but it's just not a good practice. So that's not to say that it's never okay to delete outliers, and there are a few situations where you might want to do this. So probably the most obvious ones would be when the data was just measured improperly. You know, let's say you're doing a study on adults and you ask body weight as a particular field and you see a response that has 19 pounds, that is. Well, that's impossible. There's not an adult that weighs 19 pounds, so that's probably 119, or it's probably 190 or something like that. But in those cases, if you know that the observation is erroneous and it doesn't make any sense, then you can just simply delete it without any real problem. You could also technically delete the outlier if it's not affecting the results. So going back to the previous slide, if deleting that outlier didn't change the results so strongly, then it wouldn't be such a big deal. But in this instance, it flips the results from being non-significant to being significant, and so you probably wouldn't want to do that. And the last, and this is sort of an iffy one, is if the data point of interest, or if the outlier that you're looking at, it differs from the population being studied. So if you're only studying individuals from a particular income class, and then you see somebody that's outside of that income range in your study and their values are very different, then it's probably okay to remove them in that instance because they don't fit within your study population. And the only caveat to that is that the results of your study will have to only be generalizable to the subset, just the sample you're studying, and you wouldn't be able to generalize it to, let's say, the individual that you had to remove or any groups other than the one that you're actually studying. So you lose a little bit of generalizability when you increase specificity, is another way to say that. And as I mentioned before, other solutions would be using non-parametric tests, which are generally, if you're ever not sure about something, you can always use a non-parametric test. They're great. They generally work well, and even in cases when the assumptions are met, they're still relatively powerful. So non-parametric tests are always a good fallback. And when in doubt, contact a professional. There are lots of statisticians out there and lots of services that you can contact that will help you figure these problems out. And just on a side note, sometimes outliers could be the most interesting thing about your data. What's the reason behind a value being extreme? What's the reason behind something being different from the norm? Sometimes you want to know about these things, and just cutting them off from the data and deleting them you'd lose that. So the focus should generally be on trying to understand the process that generates your data, and not necessarily making it fit a particular model or hypothesis that you want it to. Which brings me to mistake number 4, which is not accounting for multiple comparisons. So frequently, in statistics, you use this methodology of hypothesis testing. And I've listed out the 4 steps of that generally right here. So generally, you choose a significance level before you start. So let's say 0.05, which is commonly used. Then you perform your test and calculate a test statistic. So what a p-value is, it's the probability of observing that test statistic under the null hypothesis. So what that means is that, if you observe an extreme result under the null hypothesis, then it's probably not very likely. A lot of times the null hypothesis will be something like, oh, there's no difference, or the mean is 0, or something like that. It usually assumes the most conservative position. And in many cases, it's totally wrong. Like, do we believe that the null hypothesis is correct? Absolutely not. But what we're really trying to determine by using this p-value is whether or not a particular result is more or less likely than that null hypothesis. And so it's not necessarily that we're saying that the null hypothesis is true or false, which we can never really say. It's just whether or not we can look at the data and decide whether or not it's consistent with that hypothesis, meaning that we can't disprove it. So that being said, if you do notice a p-value that happens to be less than 0.05, then one of the following must be true. Either the model assumptions are not satisfied, so you're seeing a significant result based on violated assumptions. The null hypothesis is false, which is, as we just said before, probably true most of the time, but we can never really say that. Or the last thing, which is your sample happens to satisfy the conditions for a type 1 error, meaning that you observed a significant result, but in any type of probabilistic process, you will occasionally see extreme results. And it could just be that the result that you're observing is one of those times, and there's actually no effect, and what you're seeing is just the result of sampling. And if you were to repeat the study many more times, you wouldn't get the same significant result. So that's also a possibility. So the problem with multiple comparisons means that when you perform multiple tests, you actually compound this type 1 error rate. The idea that you can have a sample of data that produces a result purely by chance, and there's nothing going on there. It's just happens to be one of those cases where you get a more extreme result. So what you should do in this instance is really take into account the family-wise error rate. Now, the family-wise error rate, that just refers to the probability that at least one of your tests will give you a type 1 error. So whereas just the normal p-value and the normal significance level that you choose tells you the probability of getting a type 1 error with one of your analyses, the family-wise error rate tells you the probability of an error in at least one of your analyses. So if you run 10 t-tests, for example, the chance that at least one of those is going to give you a significant result by mistake is a lot higher than if you just run one. So as you increase the number of tests, you also have to account for that additional error that you're adding onto the analyses. So it's really important to include the number of tests as part of your calculations, and not just the number of tests that you report, but also the number that you even attempted. And this is actually a big problem in several fields. Some people might refer to it as data fishing or data dredging, where there's really not a whole lot going on with the data, but the researcher just throws tens of analyses at a particular sample until they come up with something significant, and then they publish it. And that's really not such a good practice, and it tends to degrade the quality of research. It makes it to where it can't be repeated in the future, and it causes all kinds of problems. So what can you actually do about it? Well, there's not really a simple approach for it, but one thing you could do would be something like a Bonferroni correction, for example, which is it's a time-tested method. Some might criticize it these days, but what it does is that you basically take the number of analyses you conducted and you divide up your significance level amongst all of those analyses. So I've given an example here. If you're conducting 5 t-tests and you're using a significance level of 0.05, then the Bonferroni corrected significance level would be 0.01 for each. So it really doesn't change anything about the calculations. You can do the same analyses that you always would, except you change your definition of what is considered significant, and you lower that number to account for the fact that you've done more tests. It's a little bit too conservative when you have a lot of tests, but if you don't have any other option available, then you can definitely use it. And also consider the context. Some fields and some fields of study, it may be worse to fail to make a claim than to make a false claim. So just consider the implications of what making a false claim might mean, or whether or not you would want to be more conservative in your interpretation. So no one can really tell you this. It's really up to you as the researcher to decide how to balance that. But definitely failing to account for it at all would be a huge mistake. Okay, the fifth mistake that I've decided to speak about is really one I'm sure that you've heard of before, which is relying too much on statistical significance. I'm talking about those p-values that we were referring to earlier. So there's a huge controversy in the academic community about p-values and what they're used for and what you can do with them. So, and I would go as far as to say that's the single most common statistical mistake, is the misinterpretation of p-values. It's common enough that actually the American Statistical Association issued a statement regarding p-values last year, which you can read about here at this link if you care to do so. And essentially what they say in this article is that p-values taken alone are basically not good enough to base business or policy decisions on. A p-value doesn't tell you very much about whether or not a null hypothesis or any given hypothesis is true or not, and is really only used at a high level to indicate whether or not a result should be investigated further or perhaps even repeated multiple times. So the problem with p-values is that they're based on certain assumptions, and when the assumptions are neglected, the p-value becomes meaningless, essentially. And to illustrate that, I've given you a little bit of a sample right here that I generated earlier. So don't pay too much attention to the code if that seems confusing to you. I'll explain it. All I'm doing is I'm generating 3 samples from a normal distribution, and I'm just increasing the sample size each time. So the first time I generated 10 observations, the next time I generated 100, and then I generated 1,000. And then I performed a t-test to test the difference from 0. And what you can see with this image on the left is that as the sample size increases, the significance level, or the p-value, actually gets much smaller. So what that means is that even though we generated data from the same distribution with no differences whatsoever, it's the same distribution for all 3 of these, just by increasing the sample size, we changed what we determined was significant or not. And so this just goes to show you how maybe a p-value isn't the best measure of significance all the time. And I know that having significance is, we as human beings tend to like concrete answers like that. We want a yes or a no. Is something significant or is it not? Is something yes or is it no? Well, in this case, a p-value is not necessarily bad if used properly, but you should also supplement it with something like an effect size. So let me move on to the next slide here. So it's really important to distinguish between statistical significance and practical significance. So the statistical significance is, as we've said before, it's usually measured by something like a p-value, which tells you, how likely or unlikely your result would be given a certain hypothesis. But practical significance is something totally different. With large sample sizes, even the smallest deviation can produce significant results, but it's really relative. I mean, that doesn't mean anything really, depending on your study. I mean, you really have to quantify what you consider to be a large enough difference to matter, and then not worry so much about whether or not it's statistically significant, as long as you can quantify that result with an effect size of some kind. So an example of that would be Cohen's d for the t-test, for example. Cohen's d is a measure of effect size that tells you whether or not the difference between two means is actually large or if it's relatively small. As a general rule of thumb, you need much larger sample sizes in order to be able to show statistical significance with a smaller difference. So if you have a huge difference between means, you probably don't need that many observations to be able to show that. But if you have a very tiny difference, you're going to need hundreds or maybe thousands of observations to be able to statistically show that that tiny difference is meaningful. But in many cases today, we deal with data sets that have many hundreds of thousands or millions of observations, especially in some fields of research. And so when you're dealing with sample sizes that large, everything is significant. And so essentially the p-value becomes meaningless, and you're left with only the ability to determine whether or not something is practically significant or not, and whether or not it actually matters. And that's generally a much better way to look at statistics in general. Chasing p-values is really sort of looked down upon, and in many cases, you end up just publishing bad material or something that really isn't true if you only base your decision on whether or not a p-value is less than a specific value. So that being said, the last thing I have to say is really on a much lighter note, which has to do with overcomplicating the analysis. I think that a lot of novice researchers these days tend to think that simple tests aren't as academically valid as maybe more complicated ones. Here at Statistics Solutions, we see this a lot actually, where people will think that they have to do something that's grandeur and very complicated in order to make their study seem more academically valid or accepted by others. But in reality, that's sort of the opposite of what you want. There's this tenet called Occam's razor, which I've stated here, which says that among competing hypotheses, the one with the fewest assumptions to be selected. What that basically means is that if everything else is equal, you should just choose the simplest method that's available to you. So when selecting a statistical analysis, you shouldn't really go for a sophisticated mixed model when just maybe a t-test will work out. Don't try and go for the most complicated analysis you can just because you can. You should try and choose the simplest possible test that will still solve your problem. Not to mention that if you choose a more complicated analysis, you're probably going to have a harder time defending and supporting that analysis and collecting the appropriate data in order to be able to use it, because more advanced analyses usually have more complicated assumptions or additional parameters that have to be estimated, and you may end up having to collect even more data or have more stringent sample size requirements in order to pursue that. So that's really all I have to say. I'll use this time to sort of conclude and go over everything that we've talked about, and then I'll answer a few questions. So in the data collection portion, we talked about how you got to make sure that the data that you collect allows you to actually explore the question that you're asking. And so I use the example of aggregate data versus unit level data, and to make sure that you are actually collecting data that gives you the necessary information as opposed to collecting data that you can't really do anything with. So although assumption tests are extremely important and many classical methods rely on them, you shouldn't really focus too much on the result of a hypothesis test for an assumption, and you should really look at things on a more high level and try and determine whether or not that particular assumption is violated in the sense that it will affect your results, or if the results wouldn't be affected by what you're looking at. And visual methods are usually the best because although they're subjective, you can usually get a really good idea really quickly about whether or not an assumption can hold and be perfectly valid or whether or not it can't. So whenever you're dealing with outliers, definitely don't immediately resort to deleting the extreme values. That's probably not a good idea. If you really are just not sure about it, run a non-parametric test because those hold in many, many cases. When you're performing multiple comparisons, always account for the family-wise error rate. Just remember that you're not just doing a single test here, you're doing a lot of tests, and you just have to account for the fact that you're increasing that type 1 error rate. Remember that statistical significance doesn't mean practical significance, and you should use effect sizes in conjunction with p-values to help establish the magnitude of your results and their importance. And then last but not least, make sure that you're choosing the simplest model that will answer your question, and don't go above and beyond and try to have some complicated analysis when there's really no need or no reason for it. So with that being said, I think I'll move on to some questions. Okay, so let's see, we do have some questions coming in. So Karen asked about outliers and if there was another term. I'm not sure if there's another term for outliers. Generally speaking, that's what most people call them. However, what you might see is a difference in how people define what an outlier is. And in reality, there's no fixed definition. Some people will throw out a number and they'll say, oh, an outlier is any value that's greater than 3.29 standard deviations from the mean or something along those lines. And you can use rules of thumb like that, but generally speaking, an outlier is just a point that looks different than the main group of data, and that might be different for different samples. So it just kind of depends. But generally speaking, they're usually always called outliers. That's what I normally hear them called. Although maybe sometimes incorrectly so, because sometimes a distribution just happens to have a large standard deviation or a large variance, and you just see extreme values all over the place. That doesn't mean they're outliers. I mean, the endpoint has to be somewhere. And sometimes it just distributions just happen to produce extreme values. So let's see. Okay, let's see. Linda wants me to review what I said about the mixed method study. Okay, so what I was talking about when I mentioned mixed methods was not overcomplicating your model. What you want to do when in any area of life, actually, not just statistics, is try and keep things simple. Simple is better. Just because something is more advanced or more complicated doesn't mean it's better. And when it comes to statistics especially, simpler is better because that means it's easier for you to defend, it's easier for you to conduct, it's easier for you to write about. If you have a simpler analysis, it just makes your whole life easier. So when it comes to selecting a statistical analysis to examine your data, you want to choose an analysis that answers your question, but is also as simple as you can get. And so what I was referring to was, in the case of the mixed model, is that you can use a mixed model to analyze anything that you could use to analyze a t-test, for example. But if a t-test will answer your problem, will answer your research question, you probably shouldn't go with the mixed model, simply because it's way more complicated. A t-test is nice and simple, relatively few assumptions, relatively easy to conduct, definitely easy to interpret. A mixed model, although you can conduct a mixed model and get essentially the same result, it's much more complicated. You have to estimate more parameters. There's more sophisticated assumptions that apply. And so you don't want to put yourself in a position to have to jump through a whole bunch of hoops and jump over hurdles for an analysis that really is unnecessary to answer the problem that you have. Okay, let's see. Oh, does the ANOVA account for, this is from Christy, does an ANOVA account for multiple comparisons automatically? So, Christy, actually, no, an ANOVA doesn't do that automatically. Some software packages like SPSS will give you the option to turn on certain things, like I believe SPSS offers something called two-key comparisons, which is a method of adjusting the p-value, similar to Bonferroni, actually. They're akin to the same type of method, which allows you to adjust the p-value so that you don't make mistakes. So yeah, there's definitely methods in modern software packages that will allow you to do this, but by default, the ANOVA doesn't actually incorporate this. And multiple comparisons, remember, that the ANOVA is a separate thing. Normally, multiple comparisons would be something like you conduct an ANOVA on some dependent variable and then some independent variable that has 3 or 4 levels, and then you you conduct t-tests between each pair of those levels. So those t-tests would be considered the multiple comparisons. And that's specifically what what you have to watch out for. Maybe if you just ran the initial ANOVA and stopped, you probably wouldn't have to worry too much about it. But if you're going to run the ANOVA and then you're also going to follow up by running multiple t-tests between each pair of levels, you should probably apply some type of correction, because you're dealing with one sample here, one set of data, and it's not independent, and so there's no reason to believe that these individual tests will be independent. And so when you run multiple tests on the same sample of data, the chances that one of them is going to turn up significant needs to be accounted for. So sure thing, Christy. I think that's all the questions we have, unless anyone has any more. But I'm happy to answer them over email. So thank you all for attending, and have a good day.